All right, our next topic is rolling motion and then something we call rotational energy. I want to caution straight at the outset, while we'll derive rotational energy involving things that are rolling, and we'll talk about it in that context a lot, it will be applicable for anything that's revolving, whether or not it's rotating or rolling along a surface. All right, when an object in contact with a surface rotates about an axis that itself is moving, we name that type of motion rolling. In other words, we use rolling exactly the way that you would use rolling in English. This is just the formal definition. Here we have a time-lapse picture of a cylinder that has a light in its center and a light on a rim. And we can see that the light on the axis, on the center, just kind of moves in a straight line. But the light on the rim undergoes very complicated motion, which is mathematically called a cycloid. It has some clever parametric representations, so you might run into it in a math class later on. Anyway, it's pretty complicated and annoying, but luckily we can usually treat the rotation and translation independently. We'll concern ourselves only with cases of rolling without slipping. That is, when there's no skidding involved. If you think about like a car skidding across the road, the wheels are spinning, but they're also sliding against the ground. We don't want that. We want this to be nice, smooth rolling. So we can take here and we look here and say we have this little cycloid, the path taken by an object on the rim, and this, of course, this thing spinning. And we can see that this point must track out one circumference. All right, exactly one revolution of the wheel. So delta x, which is going to be just v times delta t, has to be 2 pi r. But by definition, the time to make one for a revolution is the period t. So we end up having that the velocity, which is delta x over delta t, is 2 pi r, one circumference, over one period. And then we can group this as 2 pi over t times r, and 2 pi over t is omega. You might remember that back from the oscillations chapter. So we get that the velocity is omega r. That's one way of getting this point, that the center of mass must move forward at omega r to make this work out. Now, if we were moving along at the same speed as the wheel, we wouldn't see the wheel roll. We'd see it spinning, quote unquote, in place. Of course, it wouldn't really be in place, but it would seem like to us the center wasn't moving. And each point on the wheel, on the rim, would have a speed omega r, because anything rotating around a center has a tangential speed omega r. We've proven that a couple times so far. But the contact point would have that speed directed in direction of velocity, which is directed backward. In other words, in the rotating case, we have on the rim we have omega r no matter where you point it, but that means down here it's omega r in the negative direction. If we add that speed to the speed of the wheel's center, that point ends up getting a speed which is 0. And there's a typo here, which we should fix. A speed of 0. Not omega 0, but a speed of 0. That's a glitch in your textbook. But if the contact point has a speed of 0, it isn't moving. And that's why we call this rolling without slipping. In fact, we often think of it the other way. Because we want that point to be at relative rest, then we have to have that the forward motion of the wheel is omega r, counteracting the backward motion of the rim. Of course, an instant later, that point is no longer in contact, and it continues to move, but a new point has come into contact, and at that new moment, that new point is at rest. Whatever point happens to be touching the ground will also happen to be at momentary rest. It doesn't stay at rest, there's an acceleration going on, but it has happened to come to rest. Same way that when you throw something in the air, it can come to rest for a moment and then move on. Okay, so a wheel rolls without slipping, which is the correct velocity vector for point P on the wheel. Point P is this point here. You take a trip at 60 miles per hour, which conveniently is given to us as 27 meters per second, and the tires on your car have a diameter of 0.60 meters. What is the angular speed of your tires in radians per second? Well, remember that r, center of mass velocity, is the radius times omega. So omega is v over r, but then r is 1/2 the diameter. So it's 2v over the diameter. 2 times 27 meters per second over 0.60 meters. And this turns out to be 90 radians per second. All right, this will lead us into something called rotational kinetic energy. The atoms of an object that is spinning are still moving. Even if it's spinning in place, the atoms are still moving. Thus, there must be some kinetic energy. Kinetic energy, in this case, we have several points on what looks to be a windmill. And the kinetic energy of particle 1 is, of course, 1/2 m1v1 squared. And the kinetic energy of particle 2 is 1/2 m2v2 squared. Duh. But the linear speeds are connected to the angular speed by v1 equals omega r1 and v2 equals omega r2. But here's the crux. For a rigid object, the omega is the same for all atoms. So the total kinetic energy would be 1/2 m1v1 squared plus 1/2 m2v2 squared. Duh. But then I replace each of those with omega r. I square out everybody. I factor out everything that isn't an m1 or an r1, etc. In other words, all the things without subscripts. And I end up with the 1/2 comes outside, of course. And the omega square comes out, and I end up with something like this in between, m1 squared plus m2 squared. But we recognize that as the rotational inertia I. So the kinetic energy is 1/2 I omega squared. I only did this for 2 atoms, but you could do it for any number of them. In all cases, the masses and radii would be different, but the omega would be the same. So we'd end up with just a sum of mi ri squared, which, as we said before, is the rotational inertia of the object. Notice that our expression is exactly what we'd expect if we start with k equals 1/2 mv squared and replaced everybody the rotational equivalent, replaced m with I and v with omega, and we get the same place. But be careful. The rotational kinetic energy is not a new form of energy. It's just plain old kinetic energy. It's just dressed up a little bit differently. It's written in some more convenient form. So it isn't a new place that energy comes from. It's wrapped up in what we used to call the kinetic energy. To distinguish it from what we studied earlier, our usual kinetic energy is now called translational kinetic energy. And if the axis is moving, like for instance with a rolling wheel, the object would have both. The actual kinetic energy would be a sum of kinetic energy of translation plus kinetic energy of rotation, or K would be 1/2 mv squared plus 1/2 I omega squared. As an example, a solid cylinder is rolling without slipping across a level surface at 2.4 meters per second. The cylinder has a mass of 3.3 kilograms and a radius of 25 centimeters. What fraction of its total kinetic energy is rotational? Recall that the rotational inertia of a solid disk is 1/2 mr squared. I suppose also let's remember that a solid disk and a solid cylinder are functionally the same for rotations, because our disk can be stretched out into a cylinder without changing the distances from the axis. So again, what fraction of the total kinetic energy is rotational? Probably what we want to do is figure out what our rotational energy is and compare it to our total energy. The translational energy, of course, is still just 1/2 mv squared. And the rotational energy is 1/2 I omega squared. We plug in for I, and we have 1/2 mr squared. We plug in for omega, which is v over r. And we do this, we still have the half lying around. So we find that the rotational energy is 1/4 mv squared. Right. In this case, solid cylinder rolling without slipping. Notice we were able to connect omega to v because of the rolling without slipping. The total energy, of course, is just their sum. So we have 1/2 mv squared plus 1/4 mv squared, or 3/4 mv squared. And therefore, the fraction that's in rotations is kinetic energy of rotation over total kinetic energy, 1/4 mv squared over 3/4 mv squared, or 1/3. Notice that the radius happened to drop out. This will happen a lot when the object is rolling without slipping because of that connection between r and v and omega. Also notice the mass has dropped out, which is not surprising, which means that any solid disk that is rolling without slipping has 1/3 of its energy in rotations and 2/3 of its energy in translation. All right, consider a hollow cylinder of the same mass and radius. Which of these statements would be true about the fraction of its total kinetic energy that resides in rotations? Recall that the rotational inertia of a hollow cylinder is mr squared rather than 1/2 mr squared. So is it true that the fraction would be more than 1/3, or still equal 1/3, or less than 1/3? In this case, we can just find k rotation. K rotation is going to be 1/2 I omega squared, which is 1/2 mr squared v over r quantity squared, or 1/2 mv squared. And so we can see that that's equal to the translation, which means it's half of the total energy, which is more. And that will be a general truth. Objects that have larger rotational inertias will end up storing a larger fraction of their kinetic energy in rotation. It's hard to get them moving, and then it takes more energy to get them moving at that speed, so they store more energy in that speed. Alright, so we take a hollow sphere, a solid sphere, and a thin hoop are simultaneously released from rest at the top of an incline, which will reach the bottom first, and assume all objects are of uniform density. It'll turn out that the solid sphere arrives first, the hollow sphere arrives second, and the hoop arrives last. That's shown kind of nicely in this attached video, and I strongly recommend that you watch it. That same video, the whole 6 minutes, is a good explanation of the whole topic again if you want a different vantage on it. But for us to explain it here quickly, the larger the rotational inertia, the larger the fraction of energy that is tied up in rotation, so the smaller that is available for linear motion. Thus, objects with larger I will be slower at the bottom of the ramp and therefore arrive later. You can also think of it this way. Objects with larger rotational inertia are harder to spin, so it's less effective how their torque will be. That means a smaller angular acceleration, because the torque is less effective, so the final angular speed was less, but the angular speed is directly proportional to the linear speed, so objects with a larger rotational inertia will be slower at the bottom of the ramp and therefore arrive later. On the next page, I'll prove this algebraically in case that little bit of reasoning sounds fuzzy to you. Note that the rotational inertia can be expressed as I equals k mr squared for each thing, where for the hollow sphere k is 2/3, for the solid sphere k is 2/5, and for the hoop k is 1. This is not something you're expected to know offhand, and you don't need it to reason to this, although it helps. This is the kind of thing you could look up. But if we want to get quantitative, we will need to use actual quantitative stuff. And it turns out that these are the relative facts, that a sphere has 2/5, a solid sphere has 2/5 mr squared, a hoop has mr squared, and a hollow sphere has 2/3 mr squared. It's between the two. The analysis will be the same for each now that we've done with a k, that the energy at the top of the ramp has to equal the energy at the bottom of the ramp. So the potential energy at the top of the ramp, because it's released from rest, so there's no kinetic energy there, has to equal the translational energy at the bottom of the ramp, because there's no gravitational energy there, with us taking the usual and logical decision that we have the thing is being released from here with some velocity, ending up down here from some height, and has mass, I guess, m. So we see that mgh, wrong h, is equal to a half mv squared plus a half I omega squared. We replace the I with k mr squared. Remember, k is just some constant out front. And we replace omega with v over r. So we get, then we can cancel out the m's, which is nice. And we get gh is 1/2 v squared plus 1/2 k v squared. Factor out the half and cross multiply. Divide by factor out the v squared. Divide by the 1 plus k. And we get the velocity at the bottom is square root of 2gh 1 plus k. So we can see that the larger k is, the larger this denominator, the smaller the velocity. And the thing that's going slower will arrive last. All right, a beach ball, r equals 0.7 meters, and a marble, r equals 0.05 meters, are released from rest at the top of an incline at the same moment, which reaches the bottom of the ramp first. Here, our important thing is that this is hollow, and this is solid. So this has a larger I, and this has a smaller I. And we just said that the thing with the smaller I gets there first because less of its energy is wrapped up in rotation, so more of it can be in translation, and so it's going faster, so it gets there first.